point? What's the point of graphs? If you have an idea about what's the point or what's the reason that we draw graphs, what do you think? Rylan, go.
To record our data.
To record our data. What else? Joe, anything else?
I was saying analyze data.
Analyze data. Good. Anything else? Want to add, Cora?
I was going to say so we could, like, read it easier.
Okay, good. All good points. Okay, it allows us to record our graph and it allows us to see patterns in our data. That's really a really important part. It allows us to see trends. Do you know what I mean when I say trends?
Yeah.
Okay, is it increasing? Is it decreasing? All that kind of stuff. That's what trends mean. What is the pattern of our data? That's really the most important part of graphs. Because you can put your data in a table and you can analyze it, but putting it into a graph allows us to see, like, is there a clear high point? Is there a clear low point? Is there something that's inconsistent with our data? All that kind of stuff you can really see in a graph. So that's kind of the point of graphing, okay? So here are some things that all graphs need. All graphs must have a title, axes, labels, and a correct scale. Okay, so you're going to hear me say that a few different times, okay? On your notes sheet, you should be filling these things in as we go. Okay, all graphs need a title, axes, labels, and a correct scale. So on your graph, on your slide, I tried to make them a little bigger for you this time. Does that work a little bit better?
Yeah.
Okay, so you will see that it has a title. It tells us what's happening in this graph. This graph in particular is measuring temperatures in New York City. So if we had to look at our axes label, this one says that this axis is being labeled in degrees, and this axis is the different days we measured it. Now, who can tell me which one of these is the x-axis? Which one's the x?
The 0, 20.
What do you think? Raise your hand. Tell me, is it the one that goes up and down or the one that goes horizontal? Just say it together. What do you think?
Up and down. Horizontal.
It's horizontal.
Oh, yeah.
This is x.
Oh, yeah.
This is y. Okay, so x is horizontal. X is going to lay flat, and y is up and down. Okay, so the y goes down the axis like that. Okay, so you can think about it like that. The y goes down the axis. Okay, so on the vertical axis. So when I say vertical, do you know which one I'm talking about? Vertical is up and down. So on the y-axis or the vertical axis, it's measuring degrees. And on the x-axis or the horizontal axis, we're measuring the days, right? These are the different days. On day 1, it was 40 degrees. On day 2, it was 43 or whatever it might be, okay? So that's the axes labels that we're talking about. We have x and y, or you can also call them horizontal and vertical. Now, when we say correct scale, do you have any idea what that means? Correct scale? Yeah, what do you think?
Like the correct, the scale, like the correct. No, I don't
It's
know
okay.
how to say it, explain it. Like,
So we want, the correct scale means that we've got our numbers positioned along the axes to use as much of the graph as we can. So here's what I'm talking about. If I was going to label my graph and I chose my scale on my y-axis to be 0 to 50 to 100 to 150 to 200, my graph would all be down here. Wouldn't you agree with that? And that would not give us a very clear picture of what was happening with the temperature. The scale that we use, I want you to make a little note here. The scale that we use allows us to see the most detail in our graph. Okay, so by choosing the correct scale, it allows us to see the most detail that we can. Okay, I also want you to know we want our graph to take up, we want our data to take up most of the graph. We do not want a graph that looks like this. Let me just undo that. Okay, we don't want a graph. If this is my scale, I'm going to get rid of this green line for a second. Okay, if this is my graph, I don't want all my data right there, and my graph stops right there. Right? I don't want all my data in a tiny corner of the graph. I want it to be zoomed in so I can really see the detail in my graph. Does that make sense? So if I was making a different scale for my y-axis, I measured 6 days worth of data. It would not be smart for me to have my x-axis go from day 0 to day 10 to day 20, right? Because I only measured 6 days, so my graph would stop right there. Right? That would be really silly. So make sure that when you draw your graph, you want it to take up the whole space that you have. Does that make sense? So on correct scale, I want you also to write take up the most space. take up the most space. Sorry, my handwriting's a little crazy today. We want it to take up the most space on our graph that we can. Does that kind of make sense? We want it to be a really clear picture. We want to see the detail in our data. We don't want it to be this little blob of a line down in the bottom. Okay? All right. A couple other things in how we interpret graphs. The first vocabulary term, I don't know if you've heard these terms before, interpolate and extrapolate. Have you heard those verbs before? No. Interpolate and extrapolate. These might be new words for us. So, interpolation. We are going to interpolate a graph. Interpolation means we make predictions within recorded data. Within our recorded data. Okay? So that means, I'm going to give just a kind of a brief example of what I'm talking about here when I say that. If I have a graph that's measured at 10 and 20 and 30 and 40, and I go, I don't know, 10, 20, 30, whatever it is, right? I'm making my axes, but if I had a graph that looked like this and I asked you, well, what happens on day 25? You would be able to make an estimate by going to find that point on your graph, because that's within your data set collection, right? It's within the data you already collected. You didn't collect exactly that point, but it's within the data set we collected. Okay, extrapolation, on the other hand, is making predictions about data that's not yet recorded. So what extrapolation would look like in my example, right? Let's say we stopped recording data at day 40. I would say, well, what's your prediction for what happens at day 50? You would come say, okay, well, 50 is about here, and that means that 50 might be about here, right? That's outside of my realm of information that I collected. So extrapolation means I'm going outside of what I know, and interpolation means that I'm going to make a prediction within the data I've already collected. Does that make sense? So the difference really is that word, within and not yet recorded. Or you can say making predictions about data outside of what we've collected. Okay, outside of collected data. That might be a little bit better way to say that. Outside of collected data. Those are two kind of important vocabulary words, being able to interpolate and extrapolate data. Okay, it's really kind of simple. It's just a prediction, right? And sometimes we can predict within the data that we have, and sometimes we'll predict outside of that data. All right? But those are two kind of important skills to be able to know how to do. All right, line graphs are the types of graphs we're going to start with first. Line graphs are used when one variable affects another, the independent variable and the dependent variable. Oops, sorry. Okay, the independent variable and the dependent variable. We talked about those a little bit in our scientific method section. Okay, not sure why we're not going back here, but line graphs are used when one variable, which is the independent variable, affects another. That's the dependent variable. Okay? Okay, so I'm going to give you another kind of definition here. The independent variable is what we control. And the dependent variable is what, can anyone complete that for me? What is the dependent variable? Not what we change, that's the independent variable. What we change is that. So what's the dependent variable? What we observe, good, or what we measure. Okay? The independent variable is what we control or what we change. The dependent variable is what we're measuring. Okay? These line graphs in general are the most useful for predicting trends. They allow us to see a really clear picture of what goes on, usually over time. Okay, line graphs are usually used to give us some sort of assessment about time. As time goes on, as weeks go on, as the seconds go on, whatever it is, it usually is going to be a good measure for us as time changes. It's also something that we use when temperature changes. So if you're in the lab and you're recording data as temperature is rising, you'll be able to see what happens to that data as the temperature rises. So you'll see either time or temperature a lot of times on the x-axis. Okay, so here's a basic line graph. Did we talk about where the independent variable goes on a line graph? Yes or no? Okay, independent variable on a line graph. An independent variable goes here on the x-axis. Okay, so I draw a little I to help me remember. Independent variable goes there, and the dependent variable goes there. Okay, so on the x-axis is going to be the independent variable. On the y-axis is going to be the dependent variable. Okay, and then the way you name a line graph, the way we name a line graph or give it a title, so the name/title of a line graph is usually going to be whatever the dependent variable is versus whatever the independent variable is. I did not spell that right. How about that? Is independent spelled right now? Okay. Hopefully. That's going to be typically how we name line graphs. So if I'm measuring a change in position over time, if this is my change in position as time goes on, this would be called a position versus time graph. Okay? If I was giving that example, it would be considered a position versus time graph. Okay? If I'm going to draw the line graph, the first thing I have to do is figure out what's my numbers. What are my numbers that's going in? That's either data I collected, it's data I've been given. Right? I've got to find the numeric value of each of my variables. So I've got to figure out what's the range of my independent variable and what's the range of my dependent variable. Okay? Second thing I'm going to do is establish a scale. Establish a scale that best fits the range of data. All right, so that means I'm going to choose, is every tick mark on my graph going to be 2? Is it going to be 10? Is it going to be 100? Right? We've got to figure out what scale works best for our data. Then we're going to spread the graph out to use the most space. Be consistent throughout each axis scale. So I want to show you what I'm talking about when I say that. If I am drawing a graph, and I say my scale is going to be 10, or I don't, maybe let's say I don't establish the scale yet. I can't do this. First tick mark is 1, next tick mark is 8, next tick mark is 30, next tick mark is 65, right? Is that a consistent scale? Does every tick mark have the same change value? No. So you can't just say, oh, I've got a data point at 30, so that's going to be where my next tick mark is on my scale. That's not how it works. It has to be consistent. So if it always starts at 0, so whatever our first tick mark value is, that's what the other ones need to be. So if I decide right away that my scale is going to start from 0 and go up by 3s, I would go 3, 6, 9, 12, and I would keep going all the way up until I run out of space on that vertical axis. Okay, does that kind of make sense? All right, very good. Okay, sorry, one more thing. It says if multiple sets of data are being plotted, you can use different colors to help plot those data points. Or if you have a pencil, you could just use different shapes to plot your data points, and you would make a little key in the side. Have you heard that word before? A key on a graph? That tells you that if one of them is triangles, that's my tomato plants. If one of them squares, that's my flower plants, or whatever. Whatever it's going to be, you can use different colors or different shapes to help you plot that data. Okay, so here is an example of a graph. I want to talk about trends on the graph here, okay? But let's first check. Does it have a title? Does this graph have a title? Yes. What's the title say? Federal hourly minimum wage since inception, okay? It also tells us, does it have axes labels? Yeah, it's got the minimum wage over here, and it's got the year over here. Okay, does our axes have consistent scales? It goes up by 1, then by 2. So it's going up by 1 here. At the x-axis, we didn't start at 0 because it says since inception. So we started at 1930, but every tick mark is 10 years. So we do see consistency in that scale on the x-axis as well. Okay? Now tell me, what's the overall trend in the data here? Do we see an increase, decrease, a constant?
Increase.
We see an increase, right? We're going to be going up as we go. Okay, so it's not a constant increase. What would a constant increase look like?
A straight line.
A straight line, right? That would be a direct relationship. As one goes up, for sure the other goes up. But here we've got this kind of curved line, okay? Almost like an exponential increase. So that's just going to be an increase. It's not going to be like a constant increase, okay? All right, we already talked about naming the graph, so you can write that down again if you want to, but we did already talk about that a little bit. To see here on this graph, it doesn't look like there's any axes labels, does it? Do you see any axes labeled? Well, here they are right here. They're kind of hidden. It says the x-axis, it says this axis right here is measuring x, which is in physics measuring an object's distance traveled. And it says right here it's measured in meters. So we could even write distance there if we wanted to, okay? And then over here it says T with an S and apostrophe. So what do you think that stands for? Time, and it's being measured in seconds, right? That's what that's saying. So sometimes those axes labels can be a little bit hidden if they end up at the end of the axes. My preference would still be that it's, to the side or whatever. We also need to make sure that our unit is there as well. So we have to not only tell what's being measured, but what is it being measured in? Okay, what is the unit that goes with that?
Did you say that the distance was being measured in miles?
In meters. Just an M is meters. MI would be miles. Okay? What do we know about a direct relationship? We kind of talked about this a little bit. Direct relationship is a straight line. Any sort of straight line is a direct relationship. So straight line. You could also have a direct relationship that's in the negative direction, right? As one increases, the other decreases. Okay, those are all considered direct relationships. Okay? Direct relationship, okay, I guess I should say this. A direct relationship in kind of the way we use it does typically mean as one goes up, the other goes up. Okay, so I'm going to actually have you call a negative slope an indirect relationship here. Okay, indirect relationship means as one goes down, the other goes up. Okay, or as one goes up, the other goes down. This line is giving us an indirect relationship. Okay. All right, and then the last kind of relationship is just a constant. So as one of our axes or one of our variables changes, the other does not. Okay, as our independent variable is moving, right? Whatever we're measured in down here, maybe seconds, maybe hours, it doesn't really say. But as time goes on here, this is not changing, right? It's staying constant. So that would be any sort of horizontal line would be a constant relationship. So you might write that in there. Any sort of horizontal line would be considered a constant relationship. Okay, we're going to get into a couple different types of graphs now. The next ones are easier, I think. Bar graphs are pretty simplistic, okay? Most of the time, bar graphs are for observed data. I mean, they're counted sometimes, but most of the time it's not for a lot of trends, right? At least one of our variables is usually non-numeric. So it might be someone's favorite colors, right? We're polling that. It might be months in which something happened, right? It might be all this different kinds of stuff, but usually one of our variables is not a number. Yes. Oh, I'm sorry. Okay. In bar graphs, there's not an independent and the dependent variable. They don't depend on one another. It's just a poll that we're taking. Okay, so we're not measuring a change in anything. It's just the information we're gathering, and it allows us to look at it, okay? Bar graphs can be drawn horizontally or vertically. Which way do we usually see bar graphs? Do we usually see them drawn horizontally, or do we usually see them drawn vertically? Just what do you think?
Horizontally.
You think usually horizontally? I usually see bar graphs vertically. So I guess maybe they're more common than I think. But usually I see bar graphs that are up and down, right? That's kind of what I see.
Bar graphs are the one where you have like a line and then like you put the X's.
Look at the next page. It shows you.
Yeah, we're going to look at a couple examples.
No, the other one. The other.
These graphs are useful in comparison of items, okay, because it allows us to really see which one has more of something or less of something, okay? So comparison is an important part of that. Okay, so here's an example of a bar graph. This is how I usually see them, right, is in a vertical setting. Did I go too fast? Do I need to go back or no? I'm sorry. Yes, I can. That the y-axis here is being measured in defects per 1,000 cars. So the amount of defects reported per 1,000 cars. And then the x-axis is measured in the different factories. So what's the conclusion that you could draw? Raise your hand if you've got any conclusion that you can draw by looking at this graph. What's one thing that you can tell me by looking at the graph? Okay, yeah, Michael.
This factory does not produce good cars.
Which factory? There's three different factories.
Factory C.
Factory C has the most defects per 1,000 cars, okay? What'd you say?
It must be a Kia.
Okay. What do you think, Rylan?
Factory B has the best.
Yep. Factory B has the fewest number of defects per 1,000 cars. So those are the types of things. Bar graphs are usually used for comparison. Okay? So here's an example next of a horizontal bar graph. Okay, this is about the number of immigrants. It doesn't really say where they're immigrating to or from or anything like that. Just number of immigrants. And then it I'm sorry. It went on my screen, not on yours. Here we go. Number of immigrants. So which country is sending, we're going to call sending, we don't know exactly what else it's saying there. Which country is sending the most number of immigrants? Say it, what do you think? France. And which country is sending the fewest number of immigrants? Korea. Okay, do you see that comparison that happens there? No, none of those are dependent on one another. So there is no independent, dependent variable here. They are not causing one another to change. All right, it's just collecting that data. All right, last type we're going to talk about is pie graphs or pie charts or circle charts. There's lots of different variations of what we call this. But these pie charts are broken down into percentages. Okay, they're used when the data or categories are in the forms of percentages. You can always calculate those percentages to put them in. But basically, we take a circle, we divide it into the different portions, and then we look at them in one kind of snapshot picture. If we have data sets with a lot of categories, okay, the general rule is kind of more than 6 categories, we should use a different kind of graph because it might make our pie slices too small, right? It's hard to see it when it's too small. So here is an example of a pie chart. Sorry, do we have what we need here? Okay, all right, here's an example of a pie chart. What's our conclusion for music preference in young adults? What is it? Most people like rap. And how many people?
50%.
50% of people. What's the least common? Classical. Would you guys agree?
Yeah.
Okay, this one is a little bit tricky because the colors are hard to differentiate over here. Don't you feel like they kind of look like hard to tell the difference? But here's what one thing you can be sure of is that they need to be listed in order over here. When you put in your data into a pie chart, you should go from most all the way to least. So we should not have our 2% in between the 50 and the 25. You want your pie chart to be going in order of most to least. Okay, so when you build your pie graph, we'll talk about that, how we make that happen. But you should really list them here in order from most to least. And that will help people figure out what color goes with which one. Okay? So any questions on those types of graphing? Okay, we're going to do some practice today with line graphs.